So, if you've spent any time online watching, I don't know, engineering or just satisfying destruction videos, you've probably seen
Oh,
this.
I know exactly what you're talking about.
Yeah, it's this powder. Someone lights it and it melts through a block of solid iron like it's butter.
It really does. Looks like something out of a sci-fi movie,
Right.
but it's very real. We're talking about the thermite
The
reaction.
thermite reaction. Yeah.
And, our sources all point to this being one of the most powerful and visually dramatic chemical reactions out there. It's a real thermochemical heavyweight.
And that's what we're getting into today. We want to do a deep dive and really peel back the curtain on this. What gives it that incredible power?
Mm.
What are the hidden dangers? I've heard some pretty counterintuitive things, especially about water.
Oh, absolutely. We have to talk about that.
And then where is it actually used in the real world? Because it's not just for viral videos. It has some
Yeah.
really critical jobs, right?
It does, both in building things up and, well, in tearing them down. Our
Yeah.
goal is to really connect the science to the spectacle, to understand why this simple mix of powders demands so much respect.
Okay, so let's jump right in. The core question for me is, what is the engine here? What gives it the power to just liquefy steel?
It's all about the heat.
Hmm.
Pure, massive, overwhelming heat.
Okay.
The reaction is what chemists call fiercely exothermic.
Exothermic, meaning it releases energy, right?
Exactly. It releases way more energy than it takes to get it started. And in this case, that energy comes out as just an incredible amount of heat.
And how hot are we actually talking?
Well, the numbers are pretty staggering. You're looking at a range of about 2,500 degrees Celsius,
Wow.
all the way up to maybe 3,000 degrees.
3,000 Celsius. To put that in perspective for everyone, what does that compare to?
Okay, so think about this. Steel, your average block of steel, melts at around 1,500 degrees.
So this is double that.
It's double. This isn't just hot enough to melt iron. Our sources compare it to the temperature inside an active volcano. We're talking magma-level heat.
That explains the videos. It's not a slow burn. It's an immediate thermal shock. So, okay, the recipe. What's actually in this powder? It's shockingly simple from what I've read.
It is. It's just two things. You have aluminum powder
Okay.
and iron oxide.
Which is just rust, basically.
Basically, yeah, just
Oh.
common rust. And the magic, if you want to call it that, is just in how those two things interact.
So what's happening on a chemical level?
Right. So once you get the reaction going, the aluminum is so reactive, it desperately wants to bond with oxygen.
And the iron oxide has the oxygen.
Exactly. So the aluminum essentially wages this chemical war to steal the oxygen atoms away from the iron. It's a classic displacement reaction.
So the aluminum just muscles the iron out of the way.
Precisely. It's more reactive metal, so it wins that fight.
Hmm.
And that super fast, violent rearrangement of atoms is what unleashes all that energy.
So what are you left with at the end?
You're left with two things. Aluminum oxide, which is a kind of ceramic slag, and pure molten iron. Incredibly hot molten iron.
Ah, so the liquid that's actually doing the cutting and melting, that's the brand new molten iron that the reaction is creating on the spot.
You got it. It's making its own destructive tool as it burns.
Okay, given that insane power, I think it's a huge relief that you can't just, light this stuff with a big lighter.
Oh, no. Not even close.
Our sources really stress that getting it started is a major challenge in itself.
It is. It has what we call a high initiation energy. Both the aluminum and the rust are very stable on their own.
Right.
So you had to hit it with a ton of focused heat just to break those first chemical bonds and get the cycle going. You need like a magnesium strip fuse or a special igniter.
Yeah.
A normal flame won't do anything.
That's a crucial safety barrier then. Okay, now let's get to what I think is the most critical part of this, the thing everyone needs to know. The danger of using water on it. It just seems completely wrong. Your first instinct with a fire is throw water on it.
And in this case, that's probably the most dangerous thing you could do. You're not dealing with a normal fire. This isn't just simple oxidation.
So what happens? Why is water so bad?
Well, our sources are very clear on this. Water doesn't put it out. It actively makes the combustion more intense.
How? What's the chemistry there?
It's all about that extreme temperature. We're talking almost 3,000 degrees, remember?
Yeah.
So you throw water on that, and it doesn't just boil. It instantly vaporizes into superheated steam.
Okay, that makes sense.
But then it gets worse.
Yeah.
At that temperature, the aluminum in the reaction is so hyperreactive that it starts reacting with the water vapor itself.
Wait, what?
It literally rips the oxygen atoms out of the H2O molecules.
And what does that leave behind?
It leaves behind pure hydrogen gas.
Oh, wow.
And hydrogen gas is, as you know, incredibly flammable.
So you're not putting the fire out, you're feeding it, and at the same time creating huge amounts of explosive fuel right next to a 3,000-degree heat source.
Precisely. You're turning a very hot fire into a potential bomb. The risk of a massive secondary explosion is extremely high. It's just a fundamental lesson. You can't fight a chemical reaction with something that it can tear apart for fuel.
That's genuinely terrifying, but it gives you a real appreciation for the forces involved. So let's shift gears. This incredibly destructive power, it's actually harnessed for constructive purposes, right?
It is.
Yeah.
In fact, its main industrial use is for something very constructive. It uses the very thing we've been talking about, that instant production of pure molten iron.
Which makes it perfect for welding,
Exactly. For very specific heavy-duty welding.
like buildings or
Yeah.
ships.
Even bigger, in a way. Its most common use is for welding railway tracks together.
Ah, okay.
Yeah, they call it aluminothermic welding. You place a mold around the two ends of the rail, you set off the Thermite reaction right above it, and that pure, superheated molten iron flows down and fuses the rails together into one seamless piece.
And I imagine that bond is incredibly strong.
Much stronger than most conventional welds. It's the perfect tool when you need a portable furnace, basically. Something that brings immense heat to a remote location.
Right, because you can't exactly haul a giant industrial smelter out into the middle of nowhere.
Exactly. And beyond welding, it's also used for cutting. If you need to demolish a really thick steel beam or structure, thermite is a great way to do a very precise, very fast thermal cut.
Which, of course, brings us to its military application.
It does. It's used in specialized incendiary charges. Not really for, big explosions, but for destroying material.
How so?
They're designed to disable equipment. A small thermite charge can burn right through the engine block of a tank or melt through the barrel of an artillery piece. It uses that focused 3,000-degree heat to render enemy hardware completely useless.
It's such a strange paradox. The same chemistry that joins our train tracks together can be used to disable military vehicles.
It really highlights that chemistry itself is neutral,
Yeah.
It's not good or evil. It's just a set of principles. It's a powerful tool. And whether you're welding a rail or breaching a hull, its effectiveness comes down to expertise. Getting that ratio of aluminum to iron oxide just right and controlling where all that energy goes.
Okay, so to wrap this all up for you listening, the key takeaway here. Thermite is a simple mix. It's aluminum powder and iron oxide, just rust.
Right. And when you ignite it, that chemical reaction releases unbelievable heat, up to 3,000 degrees Celsius, creating molten iron in the process.
And the most critical thing to remember is the danger with water. Do not add water.
Please don't. The aluminum will react with it and release explosive hydrogen gas. It makes everything much, much worse.
You know, the real lesson from all our sources isn't just about the temperature or the spectacle. It's about respecting chemical energy.
Yeah, it's this powerful force that, when we understand it and handle it correctly, it builds our world. But when we're ignorant of its principles, it can be catastrophic. Knowledge really is control here.
What I find just so remarkable is how common the ingredients are. We're talking about aluminum, which is in everything, and rust, which is, well, everywhere.
It is pretty incredible.
And it leaves me with this final thought, this question for you to mull over. If two such ordinary, abundant materials can unlock this kind of extreme energy, what other powerful, fundamental chemical reactions are happening all around us every single day in materials we totally take for granted? What other potential energy is just sitting there waiting for the right key to unlock it?
That's a great question.